Welcome back. Tonight we're drifting through the story of rockets, those magnificent machines that carry our dreams beyond the sky, into the darkness where stars wait patiently. If you're enjoying these journeys into the cosmos, consider subscribing to the channel. It helps us continue exploring the universe together, one gentle fact at a time. Now, let's begin. Before we had spacecraft gliding through the void, before we had satellites whispering data across the planet, there was Cabbage Patch in Massachusetts. The year was 1926, and a man named Robert Goddard stood in that ordinary field with something extraordinary: the world's first liquid-fueled rocket. It was small, almost delicate, constructed from metal tubes and hope. When he ignited it, the rocket rose into the air for exactly 2.5 seconds. It reached an altitude of 41 feet before falling back to Earth. 41 feet. In a world where we now send spacecraft billions of miles into the outer solar system, it's easy to smile at such a modest beginning. But perhaps that's what makes it beautiful. Goddard wasn't aiming for the moon that day. He was simply trying to prove something could work. That you could mix liquid oxygen and gasoline in just the right way, ignite them, and produce enough force to defy gravity, even if only for a moment. Those 2.5 seconds contained every future mission, every satellite, every space station, every probe that has ever touched the rings of Saturn or tasted the dust of Mars. All of it began in that brief flutter above a cabbage patch, where a man dared to imagine that maybe, just maybe, the sky wasn't the limit after all. There's something counterintuitive about how rockets work, something that feels almost like a magic trick when you first learn it. You might imagine that a rocket pushes against the air to fly, the way a swimmer pushes against water or a bird presses down on the atmosphere with its wings. But that's not it at all. A rocket doesn't need anything to push against. In fact, it works better when there's nothing around it. No air, no atmosphere, nothing but the pure emptiness of space. The secret is this: a rocket pushes its own exhaust in one direction, and Newton's third law does the rest. Every action has an equal and opposite reaction. The rocket throws mass out of its engine at tremendous speed, and the universe, in its perfectly balanced way, pushes the rocket in the opposite direction. It's beautiful in its simplicity. The rocket carries everything it needs: fuel, oxidizer, structure, and it propels itself forward by essentially throwing pieces of itself backward. In the vacuum of space, where there's no air resistance to slow it down, this method becomes even more efficient. The rocket glides through the void, propelled by nothing more than its own momentum and the laws of physics that govern everything from falling apples to orbiting planets. Perhaps there's something poetic about it, that to move forward you must let go of something behind you. Imagine trying to lift something that weighs as much as 400 elephants. The Saturn V rocket, the machine that carried human beings to the surface of the moon, weighed exactly that much when it was fully fueled and ready for launch. 400 elephants worth of metal, circuitry, fuel, and human ambition, all stacked vertically on a launch pad in Florida waiting for ignition. But here's what makes it even more remarkable. 85% of that weight was fuel. Just fuel. Liquid oxygen and kerosene in the first stage, liquid hydrogen and liquid oxygen in the upper stages, millions of gallons of chemicals that would all be burned away within minutes of liftoff. The rocket wasn't really a rocket at all, in a sense. It was a controlled explosion, a carefully orchestrated burn that consumed almost its entire mass just to push a relatively tiny capsule, the part that actually mattered, the part carrying 3 astronauts, to the Moon. By the time the Saturn V reached orbit, most of it was gone, discarded in pieces across the Atlantic Ocean and floating in the emptiness of space. What arrived at the Moon was just a fragment of what left Earth. And maybe that's the nature of great journeys. You can't take everything with you. You have to shed weight, let go of what you don't need, and trust that what remains will be enough to reach your destination. More than 800 years ago, long before anyone dreamed of walking on the Moon or sending robots to Mars, Chinese inventors packed gunpowder into hollow bamboo tubes and lit them on fire. These were the first rockets, though they were called fire arrows, and their purpose had nothing to do with exploration. They were weapons of war, designed to create noise and flame, to frighten enemy horses and scatter opposing armies. The explosions were unpredictable, the trajectory uncertain. Sometimes the fire arrows would spiral wildly through the air. Sometimes they'd explode prematurely, but sometimes they'd fly straight and true, trailing smoke and terror across the battlefield. It's strange to think that the same basic principle that powered those bamboo tubes now powers the rockets that carry satellites into orbit and probes beyond the solar system. The chemistry has changed. We've moved from gunpowder to liquid hydrogen, but the fundamental idea remains the same. Contain an energetic reaction, direct it out one end, and let physics do the rest. Those ancient Chinese inventors couldn't have known that their fire arrows would one day evolve into machines capable of leaving Earth entirely. They were just trying to win battles, to survive, to protect their land. But in doing so, they planted a seed that would grow across centuries into something far grander than warfare, a way to touch the stars themselves. Perhaps that's the way with all human inventions. We create them for one purpose, and they end up serving another entirely, something we couldn't have imagined when we first struck the match. The fastest speed ever achieved by a human-made object belongs to the Parker Solar Probe, a spacecraft currently diving closer to the Sun than anything we've ever built. At its peak velocity, it travels at 430,000 miles per hour. Let that settle in your mind for a moment. 430,000 miles per hour. If you could somehow travel at that speed, you could fly from New York to Tokyo in under a minute. You could circle the Earth in about 3.5 minutes. You could reach the Moon in roughly half an hour. The Parker Solar Probe achieves this extraordinary speed not through brute force alone, but through cleverness, using the Sun's own gravity to accelerate, swinging around Venus in carefully calculated orbits that slingshot the spacecraft faster and faster with each pass. It's travelling so quickly that time itself behaves slightly differently for the probe than it does for us here on Earth, thanks to Einstein's relativity. Not enough to notice in any practical sense, but enough that the universe acknowledges the difference. And as it screams through space at this incomprehensible velocity, the Parker Solar Probe is studying the Sun's corona, trying to understand the star that gives us life, the star that makes everything possible. There's something humbling about it, that our fastest achievement, our most extreme speed, is still just a whisper compared to the speed of light, which travels more than twice as fast as the Parker Solar Probe. The universe has set limits on how fast things can go, and even our most impressive efforts barely scratch the surface of what's possible. But maybe that's okay. Maybe the journey matters more than the speed. Inside a rocket engine, temperatures reach levels that seem almost impossible. 6,000 degrees Fahrenheit, hotter than the surface of the sun itself. The metal walls of the combustion chamber glow white with heat, and the chemical reactions happening inside are so violent, so energetic, that they'd vaporize almost anything you place near them. And yet somehow the engine doesn't melt. Somehow, when it holds together long enough to push a spacecraft into orbit. The secret is cooling, but not the kind you might expect. Rocket engineers pump the fuel, often supercold liquid hydrogen or kerosene, through tiny channels embedded in the metal walls of the engine before it ever reaches the combustion chamber. The fuel absorbs heat from the metal, cooling it down, and then continues into the chamber where it burns. It's called regenerative cooling, and it's a bit like using ice water to protect your hand while you hold it over a fire, except the ice water then becomes the fire itself. The fuel serves double duty, first as a coolant, then as the energy source. Without this elegant solution, rocket engines would destroy themselves within seconds of ignition. The metal would soften, warp, and eventually fail catastrophically. But with regenerative cooling, engines can burn for minutes at a time, sustaining temperatures that would reduce most materials to puddles. There's something beautiful about the engineering, the way problem and solution intertwine, the way the same substance that creates the heat also prevents it from becoming destructive. Maybe that's true of many things in life. The source of intensity can also be the source of control if you channel it carefully enough. Most rocket engines are binary devices. They're either on or off, burning at full power or not burning at all. There's no in-between, no subtlety. But the space shuttle's main engines were different. They could be throttled, adjusted in real time like the accelerator pedal in a car. Astronauts could dial the thrust up or down depending on what the mission required, making the shuttle feel less like a pure rocket and more like a spacecraft that flew, in a sense, with some degree of grace and control. This capability was rare, even revolutionary. During launch, the shuttle's computers would constantly monitor acceleration forces, ensuring the crew didn't experience more than 3 Gs, 3 times the force of Earth's gravity pressing them into their seats. If the acceleration climbed too high, the engines would throttle back automatically, easing the pressure. Then, as fuel burned away and the shuttle became lighter, the engines would throttle back again to prevent overstressing the structure. It was a delicate dance, a conversation between machine and physics, adjusting moment by moment to keep everything balanced. And when the shuttle needed to rendezvous with the International Space Station, those engines could fire in short, controlled bursts, nudging the orbiter into precisely the right trajectory. Most rockets are brute force devices. They throw you into space and hope the math works out. But the shuttle, with its throttleable engines, felt almost alive, responsive, capable of adjustment. Of course, this complexity came with a cost. The engines were extraordinarily difficult to build and maintain, requiring meticulous inspection after every flight. But for those who flew aboard the shuttle, the ability to throttle the engines made the experience feel less like being a passenger on an explosion and more like piloting a ship through the cosmos. A rocket, when you really think about it, is a machine designed to destroy itself in the most controlled way possible. It carries enormous weight, fuel tanks, engines, a structure, and most of that weight exists only to be discarded. Modern rockets shed mass constantly during their ascent, dropping empty fuel tanks and spent engine stages as they climb toward orbit. What begins as a towering vehicle becomes smaller and smaller piece by piece, until only a tiny capsule or satellite remains. Take the Russian Soyuz rocket, for example. It has 32 engines spread across its various stages, 32 separate combustion chambers, all firing in carefully timed sequences. Within the first 5 minutes of flight, most of those engines have already burned out and been jettisoned. The boosters fall away first, tumbling back toward the steppes of Kazakhstan. Then the first stage separates, leaving the second stage to continue the journey. Finally, the third stage ignites, pushing the payload into its final orbit before it too is discarded, left adrift in space or eventually fall back to Earth. By the time the Soyuz capsule reaches the International Space Station, almost nothing remains of the original rocket. It's a philosophy of minimalism taken to its extreme. Carry only what you need and let go of everything else as soon as it stops serving you. And maybe there's wisdom in that approach, beyond just rocketry. The things that help us at the beginning of a journey aren't always the things we need at the end. Sometimes, reaching your destination means knowing what to leave behind. Words have origins, and sometimes those origins reveal something unexpected about how we see the world. The word rocket comes from the Italian rocchetta, which means little spindle, the small, cylindrical bobbins used in textile work to hold thread. Early European observers who saw rockets for the first time thought they resembled those spindles, those everyday objects from the weaving rooms and tailor shops of Renaissance Italy. And so the name stuck. It's almost charming, isn't it? That we took a word for something so domestic, so grounded in the quiet work of making cloth, and applied it to machines that would eventually carry us off the planet entirely. There's no grand mythology in the name, no reference to gods or fire or the heavens, just a simple comparison to a tool used by artisans, a recognition of shape and function. Perhaps the people who first coined the term couldn't have imagined what rockets would become. To them, rockets were curiosities, fireworks, military weapons at best. The idea that a rocket could carry a human being into space, or land a robot on another planet, would have seemed like pure fantasy. But language has a way of evolving alongside technology, carrying old meanings into new contexts. The rocchetta that once held thread now holds fuel and oxidizer. The spindle that once spun fabric now spins through the vacuum of space, carrying our hopes and instruments to places we can't reach ourselves. And maybe that's fitting. Maybe every great leap begins with something small and familiar, something we already understand, and grows from there into something we never expected. To stay in orbit around Earth, a spacecraft must travel at least 17,500 miles per hour. Not approximately, not around that speed. Exactly that fast or faster depending on the altitude. This is called orbital velocity, and it's one of the most important numbers in all of spaceflight. If you go slower, gravity wins, and you fall back to Earth. If you go faster, you climb higher into space, potentially escaping Earth's gravity altogether. But at 17,500 miles per hour, something magical happens. You fall toward Earth perpetually, but you're also moving forward so quickly that you keep missing the planet. Imagine throwing a ball. It arcs through the air and eventually hits the ground because gravity pulls it down. Now imagine throwing it faster. It goes farther before landing, faster still, and it travels even farther. If you could somehow throw it fast enough, 17,500 miles per hour, the ball would fall toward Earth, but never actually hit the ground. Yeah, because the planet's surface curves away beneath it at exactly the same rate. The ball would loop all the way around the Earth and come back to where you threw it from, still falling, still missing. That's orbit. You're not escaping gravity. You're not floating free. You're falling continuously, endlessly, but moving sideways fast enough that the ground never catches up. Astronauts aboard the International Space Station aren't weightless, because there's no gravity up there. Gravity at that altitude is still about 90% as strong as it is on the surface. They feel weightless because they're in a constant state of free fall, plummeting toward Earth while simultaneously racing forward. It's a delicate balance, a dance between falling and flying, and it requires immense speed to maintain. Perhaps that's a metaphor worth considering. And sometimes staying aloft isn't about fighting gravity. It's about moving forward fast enough that falling becomes its own kind of flight. When the Saturn V rocket lifted off from Kennedy Space Center, it didn't leap into the sky. It didn't surge upward with dramatic speed. Instead, it hesitated. The thrust-to-weight ratio at liftoff was barely above 1, meaning the rocket produced only slightly more force than its own weight. For the first few seconds, it rose almost reluctantly, climbing with what observers described as an agonizing slowness, as if the machine itself was uncertain whether to commit to the journey ahead. People who witnessed Saturn V launches often spoke about this moment with a kind of reverence. The rocket would ignite, and for a brief instant it seemed to just sit there on the pad, flames pouring from its engines, the entire structure shaking with barely contained energy. Then, slowly, impossibly slowly for something so powerful, it would begin to rise. Inch by inch at first, then foot by foot the massive vehicle would climb away from the Earth, trailing fire and thunder. It took nearly 12 seconds for the rocket to clear the launch tower, a structure only about 400 feet tall. That's slow enough that you could watch every moment of its ascent, slow enough to hold your breath and wonder if maybe, this time, it wouldn't make it. But of course it did. The engines were carefully calibrated to produce exactly this amount of thrust, because starting too quickly would have stressed the structure beyond its limits. The Saturn V needed to ease into flight, to build momentum gradually, or to let physics and engineering work together in perfect harmony. And perhaps there's something profound in that hesitation. The greatest achievements don't always announce themselves with sudden burst of speed. Sometimes they begin quietly, carefully, with a kind of measured confidence that looks like doubt but is actually precision. We often think of rockets as polluters, as machines that burn vast quantities of fuel and belch exhaust into the atmosphere. And some rockets certainly do that. Solid rocket boosters produce thick plumes of smoke and chemicals. But some modern rocket engines burn their fuel so efficiently, so completely, that the exhaust is actually cleaner than the air in many cities. Hydrogen-oxygen engines in particular produce almost nothing but water vapor and heat. Think about that for a moment. The most powerful engines ever built, devices that generate millions of pounds of thrust, that accelerate multi-ton spacecraft to orbital velocity, their exhaust is steam, pure water vapor. When a rocket like the Space Shuttle's main engines or the hydrogen-fueled upper stages of modern rockets fire, they're combining hydrogen and oxygen in a controlled explosion, and the result is H2O, the same molecule that makes up the rain falling on your window, the morning dew on grass, the clouds drifting overhead. Of course, the process also generates tremendous heat, and there are always trace amounts of other substances depending on the specific fuel mixture, but fundamentally these engines are clean in a way that seems almost miraculous. The cloud that billows out during a launch isn't pollution, it's steam condensing in the cool morning air. And when that steam dissipates, it simply joins the water cycle, the endless circulation of moisture through Earth's atmosphere, oceans, and living things. Perhaps there's irony in this. We've built machines powerful enough to escape our planet, and some of them leave behind nothing more harmful than what evaporates from a boiling kettle. The future of spaceflight might not be dirty at all. It might be as clean as rain. The largest rocket ever built stands taller than a 40-story building. SpaceX's Starship, when fully stacked with its super heavy booster, reaches nearly 400 feet into the sky, taller than the Statue of Liberty, taller than a football field is long if you stood it on end. It's a monument to ambition, a cathedral of stainless steel that gleams in the Texas sun. And yet, despite its enormous size, it's designed to do something that seems almost absurd. Land vertically on its tail fins like something drawn by a science fiction illustrator in the 1950s, who never expected their vision to become real. Rockets, for most of history, have been disposable. You launch them, they do their job, and then they fall into the ocean or burn up in the atmosphere, never to be used again. But Starship is different. It's designed to return intact, to descend through the atmosphere in a controlled fall, belly first like a skydiver, and then flip upright at the last moment, firing its engines to touch down gently on the landing pad. The Super Heavy booster does the same thing. It separates from the upper stage, flips around, and comes back to the launch site, landing on the same ground it left minutes earlier. It's a dance of engineering and physics, a routine that requires split-second timing and extraordinary precision, and when it works, when that massive tower of metal settles gently onto its landing legs, engines throttling down to a whisper, it feels like witnessing something impossible made real. The future, it turns out, looks exactly like the past's wildest dreams. Those old science fiction magazines got it right. Rockets that stand on their tails, that take off and land like skyscrapers learning to fly. That's what we're building now, and maybe that's the beauty of it. The future doesn't always look futuristic. Sometimes it looks like a dream we've been dreaming for decades, finally coming true. Here's something that might surprise you. Rocket scientists don't actually call themselves rocket scientists. The proper term is aerospace engineer. It's a small distinction, perhaps, but an important one. Rocket scientist has become a kind of cultural shorthand for extreme intelligence, for the pinnacle of technical expertise. When people say, it's not rocket science, they mean it's not impossibly difficult, not the hardest thing imaginable. But the people who actually design, build, and launch rockets rarely use that term for themselves. They're engineers. They work in teams, propulsion specialists, structural analysts, avionics experts, thermal engineers, materials scientists. They spend their days running simulations, testing components, reviewing data, solving problems that don't have obvious answers. It's meticulous work, often tedious, filled with iterations and failures and incremental progress. The term rocket scientist makes it sound almost mystical, as if these people possess some kind of innate genius that sets them apart from the rest of humanity. But the reality is both more mundane and more admirable. They're people who studied hard, who learned the mathematics and physics necessary to understand how rockets work, who developed the skills to turn abstract concepts into functional hardware. They make mistakes. They learn from those mistakes. They collaborate, argue, compromise, and iterate. The work is brilliant, yes, but it's also human, messy and uncertain and profoundly creative, and maybe that's why the term aerospace engineer is actually more fitting. It acknowledges the craft, the discipline, the engineering mindset that turns dreams of spaceflight into reality. Science gives us the principles, engineering gives us the rockets, and somewhere in between, we find people willing to spend their lives figuring out how to make the impossible merely difficult. When a rocket engine fires, the exhaust doesn't just pour out smoothly. It exits the nozzle faster than the speed of sound, and when that happens, something beautiful occurs. The supersonic exhaust creates visible shock diamonds, those stunning X-shaped patterns of light and shadow that appear in the exhaust plume, stacked one after another like geometric jewels suspended in fire. They're also called Mach diamonds, and they're one of the most visually striking phenomena in all of rocketry. These diamonds form because of the way supersonic flow behaves. As the exhaust leaves the engine, it's under tremendous pressure. When it hits the outside air, it expands rapidly, overshooting equilibrium. Then it compresses again, then expands, then compresses, oscillating back and forth in a wave pattern. Each compression creates a visible disk of brighter, denser exhaust. Each expansion creates a darker region. The result is a series of diamond shapes, sharp and brilliant, flickering in the flame. They're not solid objects, of course. They're regions of different pressure and density, visible only because of the way light scatters through the exhaust gases. But they feel almost crystalline, almost permanent, even though they exist for only as long as the engine burns. Photographers love capturing shock diamonds. They're proof that physics has an aesthetic dimension, that the laws governing pressure and velocity and supersonic flow can produce something genuinely beautiful. And maybe that's worth remembering. The universe operates according to mathematical principles. Oh yes, but those principles can manifest as art. The same equations that predict orbital trajectories and calculate thrust also paint diamonds in fire, visible for just a moment before they vanish into the sky. Most rockets are painted white, and you might assume it's for aesthetics, for visibility, for tradition. But the truth is more practical, more rooted in the physics of heat and light. White paint reflects sunlight. A rocket sitting on a launch pad in Florida or Kazakhstan or French Guiana can absorb tremendous amounts of solar energy, and that energy translates directly into heat. If a rocket were painted black, or even a dark colour, the fuel inside could heat up and expand, potentially causing tanks to rupture before launch ever begins. This is especially critical for rockets fueled with cryogenic liquids, substances kept at extraordinarily cold temperatures, like liquid oxygen or liquid hydrogen. These fuels are stored just above their boiling points, and even a small increase in temperature can cause them to vaporize, building pressure inside the tanks. White paint helps keep the rocket cool, reflecting away the sunlight that would otherwise be absorbed. It's a simple solution, almost elegantly so. No complex cooling systems, no active refrigeration. Just a choice of colour that makes all the difference. And when you see a rocket standing on the pad, gleaming white against the sky, you're seeing function disguised as form. The beauty is incidental, the whiteness is survival. Of course, some rockets do use darker colours for specific components, and some experimental designs have explored different thermal management strategies. But for the most part, rockets remain white because physics demands it. The sun is generous with its energy, but that generosity can be dangerous if you're not prepared. And maybe there's a lesson there. Sometimes the simplest choices, the ones that seem purely cosmetic, turn out to be the most important. Sometimes survival is about knowing what to reflect and what to absorb. The Space Shuttle's solid rocket boosters were remarkable not just for their power, but for their reusability. Each booster was a massive tube of solid propellant, over 140 feet tall, producing millions of pounds of thrust. And after they burned out and separated from the shuttle, they didn't simply fall into the ocean and sink. They descended under parachutes, and splashing down in the Atlantic where recovery ships would fish them out and tow them back to shore. Each booster was designed to fly at least 20 missions. Engineers would inspect them, refurbish the casings, reload them with fresh propellant and prepare them to fly again. It was one of the first serious attempts at making rocketry economical, at turning spaceflight into something more sustainable than throwing away millions of dollars of hardware with every launch. The recovery process itself was a spectacle. The boosters would arc away from the shuttle about 2 minutes into flight, tumbling through the atmosphere until their parachutes deployed. Then they'd drift down, hitting the water with tremendous force. Recovery crews had to work quickly, securing the boosters before they could take on too much water. The salt water was corrosive, and every moment the boosters spent in the ocean meant more work refurbishing them later, but it worked. Those same casings flew again and again, carrying dozens of missions into space over the shuttle program's 30 years, and in a sense, this was the beginning of the reusable rocket revolution we're seeing today. SpaceX's Falcon 9 boosters landing themselves, Starship's plans for full reusability, they all trace back to this idea that rockets don't have to be disposable, that with enough engineering and effort, we can bring them home and fly them again. The shuttle's solid rocket boosters weren't perfect. They were expensive to refurbish, and the process was labor-intensive. But they proved it was possible, and sometimes proving something is possible is all you need to inspire the next generation to make it practical. Every second a rocket sits on the launch pad, gravity is pulling it downward with a force of 32 feet per second squared. That's Earth's gravitational acceleration, the invisible hand that keeps us grounded, that makes objects fall and rivers flow downhill. For a rocket trying to climb into space, gravity is the adversary, the force that must be overcome, and every second of delay means burning more fuel just to stay in place, to fight against that relentless pull without actually going anywhere. This is why countdowns rarely pause once they enter the final minute. The rocket is fueled, the engines are ready, and every moment that passes without ignition is a moment of fuel wasted on simply existing. Once the countdown reaches single digits, the only thing that can stop a launch is a critical failure, a sensor reading that's out of bounds, a safety system that triggers something genuinely wrong. Otherwise, the launch proceeds, because the cost of waiting, measured in fuel, in momentum and complexity, becomes too high. And when the engines finally ignite, when the rocket begins to rise, it's fighting against that constant acceleration of 32 feet per second, squared with every ounce of thrust it can generate. At first, the battle is nearly even. The rocket lifts slowly, grudgingly. But as fuel burns away and the vehicle becomes lighter, the thrust-to-weight ratio improves. The rocket accelerates faster and faster, pulling away from Earth's grip with increasing confidence. Gravity never stops pulling, even in orbit. Then even on the moon, gravity is still there, still exerting its influence. But there's something defiant about a rocket's ascent, something that feels almost triumphant. The moment when thrust exceeds weight, when upward motion becomes inevitable, when the machine proves that yes, we can escape, even if only for a little while. Not all rocket engines are created equal. Some produce millions of pounds of thrust, enough to shake the ground and rattle windows miles away. Others produce thrust equivalent to the weight of a single sheet of paper. Ion drives, used on deep space probes, fall into this second category. They accelerate ions, electrically charged atoms, and expel them at tremendous speed, creating thrust so gentle you could stop it with your hand. And yet, these engines are some of the most powerful we've ever built. Whoa, in their own quiet way. The secret is time. In the vacuum of space, where there's no air resistance to slow you down, even the tiniest push accumulates. An ion drive might produce only a fraction of an ounce of thrust, but it can run continuously for months or even years. Day after day, week after week, that gentle acceleration builds. The spacecraft goes faster and faster, not through brute force, but through persistence. Eventually it reaches speeds that chemical rockets, despite their dramatic power, can never achieve, because chemical rockets burn out in minutes. The fuel runs out, and that's it. But ion drives sip their fuel, consuming it so slowly that a small tank can last for years of continuous operation. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres, or travelling billions of miles on a whisper of thrust. The Japanese probe Hayabusa used ion engines to reach an asteroid, collect samples and return them to Earth. These missions would have been impossible with traditional rockets. The fuel requirements would have been absurd, the spacecraft too heavy to launch. But with ion drives, the missions became feasible. Difficult certainly, but possible. And maybe there's wisdom in that approach. Sometimes the gentlest method, applied consistently over time, achieves what brute force never could. Sometimes patience is its own kind of power. In the early days of spaceflight, during the Cold War era when the United States and Soviet Union raced to demonstrate technological superiority, rocket failures were common. Shockingly common. Success rates below 50% were considered acceptable for early missions. Engineers celebrated when their rockets simply didn't explode, even if they missed their target orbit entirely, even if the payload tumbled uselessly into the ocean or burned up in the atmosphere. It's hard to imagine that mindset now, in an era where rocket launches are so reliable that they barely make the news unless something goes wrong. But back then, rocketry was still more art than science, more trial and error than precision engineering. The math was understood, yes, the equations of motion, the principles of thrust and aerodynamics. But translating that theory into hardware that actually worked was another matter entirely. Metal fatigued in unexpected ways, fuel pumps exploded, guidance systems drifted off course, and sometimes rockets would ignite on the pad and simply fall over. Sometimes they'd rise a few hundred feet before veering wildly sideways. Sometimes they'd appear to be working perfectly, only to disintegrate for no obvious reason, leaving engineers to sift through debris and telemetry data trying to understand what went wrong. Each failure was a lesson, a data point that informed the next design, the next attempt. Slowly, painfully, success rates improved. 50% became 60, then 70, then 80. Today, modern rockets achieve success rates above 95%, and failures are investigated exhaustively, treated as serious anomalies rather than expected outcomes. But those early failures were necessary. They taught us what didn't work, which materials couldn't handle the stress, which designs were fundamentally flawed. Yeah, the rockets that fly reliably today are built on a foundation of past explosions, past mistakes, past attempts that ended in fire and wreckage. And perhaps that's true of all progress. The successes we celebrate are built on failures we've forgotten, on attempts that didn't work but taught us something valuable nonetheless. When we say a rocket engine burns fuel, we're using a word that doesn't quite capture what's actually happening. Burning, in the everyday sense, is a relatively slow process. Wood burning in a fireplace, a candle flame flickering in the dark. But inside a rocket engine, the fuel doesn't burn. It undergoes extremely rapid chemical reactions that release energy so quickly, so violently, that the combustion chamber becomes an environment unlike almost anything else on Earth. Fuel and oxidizer mix in precise ratios, and the moment they meet, they react. Bonds between molecules break and reform in new configurations, releasing tremendous amounts of energy as heat and expanding gases. In the most powerful engines, this happens so fast that the combustion chamber glows white hot, radiating light across the entire visible spectrum. The gases expand with such force that they scream out of the nozzle at supersonic speeds, creating thrust. It's not gentle, it's not gradual, it's a controlled explosion, sustained for as long as fuel keeps flowing into the chamber. Engineers designing these engines must account for pressures that can crush metal like tinfoil, and temperatures that would vaporize most materials within seconds. The combustion chamber is a place where a matter transforms, where chemical potential energy becomes kinetic energy, where the abstract principles of thermodynamics become tangibly real in the form of thrust that can lift hundreds of tons off the ground. And perhaps there's something profound about this. We take substances that seem stable, unremarkable, kerosene, hydrogen, oxygen, and under the right conditions, we release the energy hidden within their molecular bonds. We transform them from dormant chemicals into the force that carries us beyond our atmosphere. The fuel doesn't burn so much as it transforms, offering up its stored energy in a brilliant, thunderous exchange that pushes us toward the stars. Some rocket engines can restart in space, others cannot. This might seem like a minor technical detail, but it's actually one of the most critical distinctions in rocket design. An engine that can only fire once must work perfectly the first time, because there's no second chance. The burn must be timed exactly right, the duration calculated precisely, the trajectory perfect. But an engine that can restart gives you options, flexibility, the ability to adjust your course mid-flight. Restarting a rocket engine in the vacuum of space is harder than you might think. On the ground, fuel and oxidizer flow into the combustion chamber under the influence of gravity and pressure. But in space, where there's no gravity, liquids behave strangely. They don't settle to the bottom of tanks. They float, forming spheres or clinging to the walls in unpredictable ways. To restart an engine, you first need to make sure fuel actually flows to the pumps and into the combustion chamber. Some rockets use small thrusters to provide gentle acceleration, settling the fuel before the main engine fires. Others use bladders or mechanical systems to push fuel toward the engine, regardless of which way is down. And once the fuel is flowing, the engine must ignite reliably in the cold vacuum of space, with no atmosphere to help sustain combustion. Engines that can do this reliably are engineering marvels. They're used for missions that require multiple orbital adjustments, rendezvous with space stations, trips to the moon that require separate burns to enter and exit lunar orbit, interplanetary missions that need course corrections along the way. The Apollo lunar module used a restartable engine for its descent to the moon's surface, and if the astronauts had needed to abort the landing, that same engine would have fired again to lift them back to orbit. The ability to restart wasn't just convenient, it was essential for crew safety, for mission success, for having a way out if things went wrong. And maybe that's a principle worth considering beyond rocketry. Having the ability to start again, to adjust course, to try a second time, that capability can mean the difference between success and failure, between reaching your destination and being stuck on the wrong trajectory with no way to correct it. The sound of a rocket launch is almost unimaginable until you've experienced it. We're not talking about noise in the way you usually think of it, loud music, a jackhammer, a passing train. We're talking about acoustic energy so intense it can liquefy concrete if it's not properly deflected. Sound waves powerful enough to turn sand into glass through sheer vibration and heat. The Saturn V, when it launched, produced sound levels around 200 decibels at close range, far beyond the threshold of pain, far beyond what human ears can process without permanent damage. This is why launch pads are equipped with massive water deluge systems. During ignition, these systems dump thousands of gallons of water per second onto the launch pad and into the flame trenches beneath the rocket. The water isn't there to cool the flames exactly, though it does help with that. It's there to absorb the acoustic energy, to dampen the sound waves that would otherwise reflect back up and damage the rocket itself. The vibrations from a rocket's own engines can shake delicate components apart, can crack welds, can destroy electronics. The water breaks up those sound waves, turns them into steam and turbulence, protecting the rocket from its own power. And even with the water deluge, the sound is overwhelming. People who witness launches talk about feeling it in their chest, in their bones, as much as hearing it. The air itself seems to compress and expand with each pulse of the engines. You don't just listen to a rocket launch, you're immersed in it, surrounded by pressure waves that physically push against your body. And there's something primal about that experience, something that connects to the deepest parts of our nervous system. The recognition that we're witnessing an event of extraordinary power, something that commands respect and awe. The sound of a rocket launch is the sound of controlled violence, of energy unleashed in service of a purpose, of human ambition made audible. And maybe that's fitting. The journey to space should be loud. It should announce itself. It should remind us that leaving Earth is not a casual endeavour, but an act of defiance against everything that would keep us grounded. When astronauts ride a rocket into space, they experience G-forces, gravitational forces multiplied by acceleration, that press them back into their seats with increasing intensity as the rocket climbs. At peak acceleration, they typically experience around 3 to 4 Gs, meaning they feel 3 to 4 times heavier than normal. It's about the same force you'd experience on a moderately intense roller coaster, though it lasts much longer, several minutes rather than a few seconds. 3 Gs doesn't sound extreme. Fighter pilots routinely experience much higher forces during aerial maneuvers, sometimes exceeding 9 Gs during tight turns, but the difference is duration. Since a roller coaster pulls high Gs for a moment, then releases. A rocket maintains that pressure continuously, minute after minute, as it burns through its fuel and accelerates toward orbital velocity. Your arms become heavy, difficult to lift. Your chest feels compressed. Breathing requires effort. Moving your head feels like it's weighted down. And this is during the gentlest part of the ride. Modern rockets are specifically designed to limit G-forces for crew comfort and safety. Early spacecraft pushed higher, testing the limits of what human bodies could endure. The sensation, astronauts report, is not painful exactly, but profoundly strange. You're lying on your back facing upward, and the rocket is accelerating you in that direction with relentless force. Your weight shifts from the usual downward pressure you felt your entire life to a new direction entirely, backward into your seat. And as the rocket becomes lighter from burning fuel, the acceleration increases. The G's build gradually at first, then more noticeably. By the time the engines cut off and you reach orbit, the sudden absence of that pressure feels almost as disorienting as the pressure itself. You go from 3 Gs to 0 instantly, from being pressed firmly into your seat to floating freely, and in that moment you've transitioned from one world to another, from the realm where gravity dominates to the realm where it fades into the background, still present but no longer the master of your motion. The mathematics of rocket flight, the equations that tell us how much fuel we need, how fast we can go, what trajectories are possible, were worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903. He never built a rocket himself. He never witnessed a launch, never saw his theories tested in practice. He simply sat with pencil and paper, working through the physics, understanding that if you wanted to reach space, you needed to think about mass ratios, about exhaust velocity, about the relationship between fuel and payload. His most famous equation is beautifully simple. The change in velocity of a rocket is proportional to the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. In other words, the faster your exhaust moves and the more mass you shed during flight, the faster you can go. This equation still governs rocket design today, more than a century after Tsiolkovsky first wrote it down. Engineers at SpaceX, at NASA, at space agencies around the world use his math to calculate delta-V budgets, to determine how much fuel a mission requires, to figure out whether a particular rocket can accomplish a particular task. Tsiolkovsky understood, long before anyone had seriously attempted spaceflight, that getting to orbit would require shedding most of your starting mass. He understood that single-stage rockets would struggle to reach orbit because the mass ratio requirements were so demanding. He predicted multi-stage designs, orbital mechanics, even space stations and interplanetary travel, all from pure theory, pure thought. And he did this not in some prestigious university, not in a well-funded laboratory, but in a small town in Russia. They were teaching children during the day and exploring the cosmos mathematically at night. Perhaps that's the power of theoretical work. You don't always need to build the thing to understand it. Sometimes, the equations are enough to reveal the truth, to show you what's possible, to light the path that others will eventually follow. Tsiolkovsky gave us the map. Later generations built the rockets. Some rocket fuels are so volatile, so chemically aggressive, that they ignite spontaneously the instant fuel and oxidizer touch each other. These are called hypergolic propellants, and they're both terrifying and incredibly useful. There's no ignition system needed, no spark plugs, no complicated startup sequence. The two liquids meet, and they react immediately, violently, producing thrust without any additional encouragement from the engineers. Handling hypergolic fuels is dangerous work. Many of them are highly toxic. Substances like hydrazine and nitrogen tetroxide can kill you with minimal exposure, attacking your lungs, your nervous system, your organs. refueling crews wear full hazmat suits, working with the urgency and precision of bomb disposal technicians. One spill, one leak, one moment of carelessness, and people can die. And yet, hypergolic fuels have been used extensively throughout the history of spaceflight. The Apollo lunar module used them. The Space Shuttle's orbital maneuvering system used them. Many modern satellites still use them for station keeping and attitude control. The reason is reliability. When you absolutely positively need an engine to fire, perhaps because you're trying to rendezvous with a space station, or because you need to abort a lunar landing and return to orbit before your life support runs out, hypergolic fuels are your friend. They work every time, instantly, with no possibility of ignition failure. You don't have to worry about spark plugs that might not fire in the vacuum of space, or combustion chambers that might not light properly after sitting dormant for days or weeks. The fuel meets the oxidizer and thrust happens. It's that simple, and that certainty is worth the danger of handling such nasty chemicals. Perhaps there's a parallel worth drawing. Sometimes the most reliable solutions are also the most dangerous ones. The things that work without fail often demand respect, careful handling, and awareness that convenience and risk can coexist in the same package. Hypergolic fuels will ignite no matter what. That's their strength. That's also why you handle them with such extraordinary care. The metal nozzle at the end of a rocket engine exists in an environment of almost incomprehensible extremes. On the inside surface, where the exhaust gases rush past at supersonic speeds, temperatures exceed 6,000 degrees Fahrenheit. On the outside surface, exposed to the air or the vacuum of space, temperatures might be just a few hundred degrees. That's a temperature gradient, a difference between inside and outside, of more than 3,000 degrees across just a few inches of metal. Most materials would crack under this kind of stress. Metal expands when it gets hot, and contracts when it cools, and when different parts of the same piece of metal are at wildly different temperatures, those expansions and contractions happen at different rates. The result is stress, tension, forces that want to tear the material apart, and yet rocket nozzles hold together, burn after burn, maintaining their shape and structural integrity, even as they channel the most extreme conditions humans have ever created. The secret lies in material science and cooling. Engineers use exotic alloys, metals that can withstand high temperatures without losing strength. They design cooling channels that run through the nozzle walls, circulating fuel or coolant to carry heat away from the hottest regions. They carefully shape the nozzle to minimize stress concentrations, the places where cracks would most likely begin. And even with all these precautions, rocket nozzles are inspected meticulously after every flight, examined for signs of wear, for tiny cracks that might propagate into catastrophic failures if left unchecked. The nozzle is where theory meets reality in the most unforgiving way. It's where we take the energy released by chemical reactions and shape it, direct it, turn it into thrust. And the fact that we can build something that survives in that environment, that functions reliably under conditions that would destroy almost anything else, is a testament to human ingenuity and our stubborn refusal to accept that something can't be done just because it's difficult. On a spacecraft floating through the vacuum of space, tiny control rockets called reaction control thrusters are used for adjustments, rotating the vehicle, fine-tuning its orientation, making small corrections to its trajectory. These thrusters produce so little force that you could stop one with your hand. If you stood in front of one and it fired, you'd feel a gentle push, like someone blowing on your palm. It wouldn't hurt you. It wouldn't knock you over. It would barely move you. And yet, in the weightlessness of space, these tiny puffs of gas are enough to rotate an entire spacecraft. There's no friction up there, no air resistance, nothing to slow down motion once it begins. If you apply even a small force to an object in space, it will start rotating or moving, and it will continue doing so until another force stops it. So a thruster that seems almost comically weak by Earth standards becomes perfectly adequate for controlling a multi-ton vehicle in orbit. Astronauts use these thrusters to point their spacecraft in specific directions, to align with docking ports on the International Space Station, to orient solar panels toward the Sun or antennas toward Earth. Each thruster fires for just fractions of a second, a brief hiss of gas, and the spacecraft responds, slowly and gracefully pivoting in the darkness. It's a reminder of how different the rules are in space. On Earth, we're so accustomed to fighting friction, to pushing against air resistance and gravity, that we think of force in terms of what's needed to overcome those obstacles. But in space, there are no such obstacles. The smallest push becomes meaningful. The gentlest touch can change a trajectory. And maybe there's a lesson in that about context and environments. What seems powerless in one setting can be perfectly adequate in another. The thruster that would barely move you on Earth can rotate a spacecraft in orbit. Strength isn't absolute. It's relative to the forces you're working against. The combustion chamber of a rocket engine is one of the most extreme environments humans have ever created, and that's not hyperbole. Inside that chamber, pressures can exceed 3,000 pounds per square inch, more than 200 times atmospheric pressure at sea level, while temperatures approach those found on the surface of a star. It's a place where matter exists in states we rarely encounter, where the boundary between solid, liquid, and gas becomes blurred by sheer energy. Consider what's happening in there. Fuel and oxidizer are being pumped in at tremendous rates, sometimes thousands of gallons per minute. They mix, they react. And the chemical bonds that held them together break apart, releasing energy. That energy manifests as heat and pressure, creating expanding gases that want desperately to escape. The only exit is through the nozzle, so the gases accelerate, reaching supersonic speeds as they pour out into the air or vacuum. And all of this happens in a space often no larger than a basketball. The metal walls of the combustion chamber must contain this violence, must channel it, must survive being bathed continuously in conditions that would vaporize most materials instantly. Engineers have developed specialized alloys, cooling techniques, geometric designs that distribute stress as evenly as possible. But even with all our advances, combustion chambers have finite lifespans. They wear out. The heat and pressure slowly degrade even the toughest materials, and eventually they must be replaced or rebuilt. And yet, for a few minutes at a time, they work, they hold, they transform chemical energy into kinetic energy with remarkable efficiency. The combustion chamber is where human ambition confronts the fundamental limits of material science, where we push matter to the edge of what it can endure and then ask it to endure just a little bit more. And somehow, remarkably, it does. During the 1960s and 70s in the Nevada desert, engineers tested nuclear-powered rockets. Not science fiction, not speculative designs, actual hardware that used nuclear reactors to heat hydrogen to extreme temperatures and expel it for thrust. The program was called NERVA, Nuclear Engine for Rocket Vehicle Application, and demonstrated that heating hydrogen with a nuclear reactor could create incredible thrust with far better efficiency than chemical rockets. The concept is elegant in its way. Instead of burning fuel, you run hydrogen through a nuclear reactor core. The reactor heats the hydrogen to thousands of degrees, and the expanding gas rushes out through a nozzle, creating thrust. Because you're not limited by chemical reactions, which can only release so much energy per kilogram of fuel, you can achieve much higher exhaust velocities, meaning you need less propellant to accomplish the same mission. A nuclear rocket could, in theory, cut the travel time to Mars in half compared to chemical propulsion. It could make the outer solar system more accessible, enable missions that would be impractical with conventional rockets. The tests were successful, the engines worked, they ran for hours, proving the concept was viable, but the program was cancelled before any nuclear rocket ever flew in space. The reasons were complex: budget constraints, changing priorities, concerns about launching nuclear material into orbit, the end of the Apollo program reducing urgency for advanced propulsion, and so the nuclear rockets were shelved. The test hardware placed in storage or museums, the knowledge preserved but not pursued. Perhaps one day we'll revisit the concept. The physics hasn't changed, the advantages are still real, but for now, nuclear rocket engines remain a path not taken, a technology that works but isn't used, a reminder that progress isn't always linear, and that sometimes we develop capabilities we're not quite ready to deploy. When a rocket launches at dawn or dusk, something magical happens in the sky. The rocket itself may have climbed beyond the horizon from the perspective of people on the ground, disappearing from direct view, but its exhaust plume, that long trail of gas and vapour streaming behind the ascending vehicle, remains visible. And because the rocket is now at high altitude, the plume is still catching sunlight even though the sun has set for observers below. The result is a twilight phenomenon, a luminous jellyfish shape painted across the darkening sky in colours that seem almost supernatural. These displays can be seen from hundreds of miles away. The exhaust spreads and diffuses as it climbs into thinner atmosphere, creating vast glowing clouds that reflect oranges and pinks and purples. The shapes morph and flow, evolving as atmospheric winds at different altitudes push the gases in different directions. People who've never seen a rocket launch before might step outside and see this apparition in the sky, this enormous, glowing structure that looks like nothing in their ordinary experience, and wonder if something otherworldly is happening. In a sense, something otherworldly is happening. A machine built by human hands is climbing out of our atmosphere, leaving our world behind, and the evidence of its passage is written across the sky in light and colour. These twilight phenomena are transient, lasting only minutes before the exhaust disperses and the colours fade. But while they persist, they're reminders that spaceflight isn't just a technical achievement, it's also beautiful. It's also art. The same exhaust that propels a rocket to orbit also paints the sky, creating beauty as a byproduct of function. And maybe that's worth pausing to appreciate, that our attempts to reach beyond our planet leave visible traces, evidence of our ambition rendered in light, visible to anyone who happens to look up at the right moment and wonder what that strange glow might be. Modern rockets navigate through space using some of the oldest navigation techniques humans have ever developed. Star trackers, cameras that identify constellations and calculate the spacecraft's orientation based on the positions of stars, use the same fundamental principle that ancient sailors used when they navigated by the stars, measuring angles to Polaris or the Southern Cross to determine their latitude and heading. The stars you see don't move, or rather, they move so slowly from our perspective that they might as well be fixed reference points. A spacecraft with a star tracker can look out at the cosmos, identify specific stars in its field of view, compare what it sees to an onboard catalogue of star positions, and calculate exactly which way it's pointing with extraordinary precision. No GPS satellites are needed, no ground stations, no radio signals, no connection to Earth. These stars themselves provide all the information necessary. It's navigation that works anywhere in the solar system, that functions independently, that relies on the universe itself as a reference frame. And there's something beautiful about this continuity. Thousands of years ago, Polynesian navigators crossed vast stretches of the Pacific Ocean by reading the stars, understanding that those distant lights could guide them home. Today, spacecraft crossing even vaster stretches of space use the same principle, refined and automated but fundamentally unchanged. The stars guided us when we explored our own planet. Now they guide us as we explore beyond it. Perhaps they'll continue guiding us as we venture farther still, toward other stars, other systems. The cosmos provides its own navigation aids, scattered across the darkness, patient and eternal. All we have to do is look up and recognize them for what they are. Not just beautiful lights in the night sky, but signposts, reference points, tools for finding our way through the infinite. The space shuttle's main engines were extraordinary pieces of engineering, capable of producing over 500,000 pounds of thrust each. But here's something that surprises many people. Those engines were shut down while the shuttle was still in space, still below orbital velocity. 8.5 minutes after launch, the main engines cut off, and the external fuel tank, that massive orange cylinder that held the liquid hydrogen and oxygen, was jettisoned, left to tumble back toward Earth and break apart over the Pacific Ocean. At that moment, the shuttle wasn't in a stable orbit yet. It was in space, yes, above most of the atmosphere, but moving too slowly to remain there indefinitely. Without another push, it would eventually fall back down. So after the main engine shut down and the external tank separated, there was a period of silence. Complete silence. The roar that had filled the cabin for 8.5 minutes simply stopped. The crew floated in their seats, near feeling weightless for the first time, while the orbiter coasted upward on momentum alone. Then, after a brief pause, the orbital maneuvering system engines would fire, smaller thrusters on the back of the shuttle that would provide the final push needed to circularize the orbit, to add just enough velocity to stay in space rather than falling back down. Astronauts describe this transition as surreal. The violence and noise of launch, the sustained pressure of acceleration pressing them into their seats, the thunderous burn of the main engines, all of it would end abruptly, replaced by silence and weightlessness. And in that silence, coasting through the upper atmosphere with Earth spread out below and the black of space above, they'd know they'd made it. They were in space. The hardest part was over. What remained was the quiet drift into orbit, a gentle conclusion to a journey that began with fire and thunder. Rocket exhaust doesn't just push spacecraft into orbit. It can also create its own weather. The water vapor and other gases released during a launch can form clouds, and under the right atmospheric conditions, those clouds can trigger lightning. This sounds almost absurd, that a rocket could generate weather, but it's real, and it's something launch directors monitor very carefully. The exhaust plume from a rocket acts like a conductive path through the atmosphere, a column of ionized gas that can channel electrical charge. If there's already atmospheric electricity present, conditions that might lead to a thunderstorm for instance, the rocket's exhaust can provide a route for that electricity to flow, creating lightning that follows the plume upward or downward. This is why launches are scrubbed when lightning is detected within a certain radius of the launch pad, why meteorologists study atmospheric electricity with such care on launch days. A rocket ascending through electrically charged clouds could trigger a lightning strike that damages the vehicle, its electronics, its guidance systems. It happened once, during the Apollo 12 launch in 1969. The Saturn V was struck by lightning twice during ascent, once at 36 seconds into flight, again at 52 seconds. The strikes temporarily knocked out the spacecraft's fuel cells and many of its electrical systems. The astronauts, in a moment of remarkable quick thinking and calm, followed procedures to reset their systems, and the mission continued successfully. But it was a close call, a reminder that even with all our preparations, we're still launching through an atmosphere that has its own weather, its own electrical dynamics, its own capacity to surprise us. We've learned since then. We've improved our understanding of atmospheric electricity, refined our launch commit criteria, developed better shielding and grounding systems, but the fundamental truth remains. A rocket launch doesn't just happen in the environment. It interacts with it, changes it, becomes part of the weather for a brief dramatic moment before climbing beyond the atmosphere entirely. On November 26, 1965, France became the third nation in history to launch a satellite into orbit, joining the United States and the Soviet Union in the exclusive club of spacefaring powers. The rocket was called Diamant, and it launched from a site in the Sahara Desert, carrying a small satellite named Asterix into orbit. It was a modest achievement compared to the massive rockets and ambitious programs of the Cold War superpowers, but it was significant nonetheless. France had developed its rocket program largely independently, without the enormous budgets or geopolitical pressures that drove American and Soviet efforts. The Diamant rocket was small, elegant, efficient, designed to accomplish a specific task with limited resources, and it worked. Asterix reached orbit, transmitted its signals back to Earth, and France demonstrated that spaceflight wasn't the exclusive domain of the two superpowers locked in their tense rivalry. Other nations could participate, and other nations could develop the capability to reach orbit if they committed the resources and expertise. In the decades since, many more countries have joined the ranks of spacefaring nations. China, Japan, India, Israel, Iran, North Korea, South Korea, each has demonstrated the ability to launch satellites into orbit using domestically produced rockets. The club that was once exclusive to three has expanded, and with that expansion has come diversification of approaches, technologies, goals. But France was first among the followers, the first to prove that you didn't need to be a superpower to reach space. You just needed the will to try, the engineering expertise to solve the problems, and the commitment to see it through. And maybe that's worth remembering. Space isn't the domain of any single nation or ideology. It's a frontier that belongs to everyone who can reach it, to everyone willing to invest in the technology and knowledge necessary to climb beyond our atmosphere and touch the infinite. Some of the most powerful rockets ever built use kerosene as their primary fuel. Not exotic chemicals with unpronounceable names, not substances that require extreme cooling or hazmat suits to handle. Just kerosene, essentially refined jet fuel. the same basic hydrocarbon compound that powers commercial airliners. It's far less powerful than liquid hydrogen, molecule for molecule, but it has advantages that make it attractive for certain applications. Kerosene is dense. A gallon of kerosene contains far more mass than a gallon of liquid hydrogen, which means you can pack more of it into a smaller tank. It's also storable at room temperature. Thus, you don't need cryogenic cooling systems, no complex insulation, no constant venting of boil-off gases. You can load kerosene into a rocket and let it sit for hours or even days without significant loss. This makes kerosene-fueled rockets simpler in some ways, more robust, easier to handle. The Russian R-7 rocket family, which has been launching since the 1950s and still carries crews to the International Space Station today, uses kerosene in its first stage. SpaceX's Falcon 9 uses a refined form of kerosene called RP-1. These rockets sacrifice some performance. Kerosene doesn't provide the same exhaust velocity as hydrogen, but they gain simplicity and reliability. And in spaceflight, where complexity is often the enemy of success, simplicity has real value. There's something almost charming about the fact that some of our most advanced spacecraft begin their journey to orbit, burning a fuel you could, in theory, put in a lamp. The path to space doesn't always require exotic solutions. Sometimes it requires taking what works, what's proven, what's reliable, and using it exceptionally well. Kerosene has been powering rockets for 7 decades now. It's not glamorous, it's not cutting edge, but it works, and it keeps working, mission after mission, carrying satellites and astronauts and supplies into orbit with remarkable consistency. In the 1990s, an experimental vehicle called the Delta Clipper demonstrated something that seemed impossible at the time: a rocket that could take off vertically, fly to altitude, hover in mid-air, and then land on its tail fins like a spacecraft from a 1950s science fiction magazine. It looked absurd. Rockets weren't supposed to land. They were supposed to be disposable, used once and discarded. But the Delta Clipper proved the concept was viable. The vehicle itself was relatively small, about the size of a grain silo, powered by a cluster of rocket engines that could throttle up and down. It would lift off from the desert floor in New Mexico, climb to altitudes of several thousand feet, maneuver in flight, and then descend nose first, flipping upright at the last moment to touch down gently on its landing legs. Each flight lasted only a few minutes, and the vehicle never reached orbital altitudes. It was purely experimental, a testbed for technologies and techniques. But it worked. Yeah, it demonstrated that vertical landing was possible, that rocket engines could be throttled precisely enough to control descent, that a vehicle could be flown multiple times without extensive refurbishment between flights. The program was eventually cancelled, victim of budget cuts and shift in priorities. The Delta Clipper itself was damaged in a landing accident and never flew again. But the technologies it pioneered, the lessons it taught, lived on. Today, SpaceX's Falcon 9 boosters land themselves routinely, touching down on drone ships in the ocean or on concrete pads at the launch site. Blue Origin's New Shepard does the same. These modern reusable rockets owe a debt to the Delta Clipper, to the engineers who proved that yes, you could land a rocket on its tail. That science fiction could become reality if you were willing to work through the engineering challenges, and maybe there's a lesson in that about persistence and vision. The Delta Clipper program itself didn't survive, but its ideas did. Sometimes, pioneering work doesn't pay off immediately. Sometimes you plant seeds that others will harvest years or decades later. The Delta Clipper showed us what was possible. It took another generation to make it practical. The Earth rotates, spinning on its axis once every 24 hours, and because of that rotation, different points on the planet's surface are moving at different speeds relative to the center of the Earth. At the equator, the surface is moving eastward at about 1,000 miles per hour. At the poles, the rotational velocity is essentially zero. This fact has profound implications for spaceflight, because when you launch a rocket, you're not starting from a standstill, you're already moving, carried along by Earth's rotation. This is why most launch sites are located as close to the equator as geography allows. When you launch eastward from the equator, you get up to 1,000 miles per hour of free velocity. Momentum you don't have to generate with your rocket engines, speed that's already there, provided by the planet's rotation. It's not a huge amount compared to the 17,500 miles per hour needed to reach orbit, but it's not negligible either. That free velocity makes launches from equatorial sites more efficient, allowing rockets to carry slightly more payload or use slightly less fuel. Engineers even account for this when planning trajectories. The Coriolis effect, the apparent deflection of moving objects caused by Earth's rotation, influences how rockets climb into orbit, how they align their trajectories with the desired orbital plane. It's a subtle effect, one that you don't notice in everyday life. But at the speeds and distances involved in spaceflight, it becomes significant. Perhaps there's something elegant about this. We're launching from a spinning platform and we use that spin to our advantage. The Earth isn't just our home, it's also, in a sense, the first stage of every rocket ever launched. Providing that initial velocity, that head start, that rotational momentum we inherit simply by existing on its surface. We're not fighting against Earth's motion. We're harnessing it, using it, letting the planet give us a push toward the stars. The bell-shaped nozzles on rocket engines aren't arbitrary. Their shape is the result of careful mathematical optimization designed to let exhaust gases expand in a precise way that maximizes thrust. The exact contour of that bell matters enormously. Even small imperfections, deviations of just a few millimeters from the ideal shape, can reduce efficiency by several percent. Here's what's happening inside that nozzle. Exhaust gases leave the combustion chamber at extremely high pressure and relatively low velocity. As they flow into the nozzle, they expand, trading pressure for velocity. The nozzle's shape guides this expansion, allowing the gases to accelerate smoothly, converting thermal energy and pressure into kinetic energy, into speed. If the nozzle is too short or too wide, the gases won't expand fully and you'll lose efficiency. If it's too long or too narrow, the gases will overexpand, creating shock waves and turbulence that waste energy. The ideal nozzle shape depends on the altitude at which the rocket is flying. At sea level, atmospheric pressure pushes back against the exhaust, so you want a shorter nozzle. In the vacuum of space, where there's no atmospheric pressure, you want a longer nozzle to extract maximum performance. Some advanced engines use nozzle extensions that deploy after launch, adapting to the changing conditions as the rocket climbs. Others compromise, using a single fixed nozzle optimized for average conditions throughout the flight. And all of this matters because rocket performance is measured in percentages. A few percent improvement in efficiency can mean the difference between reaching orbit and falling short. Between carrying enough payload to make a mission viable and coming up just a bit too heavy. The nozzle is where theory becomes hardware, where the equations of gas dynamics manifest as shaped metal that transforms hot gas into thrust. Get the shape right and you have an efficient engine, Get it wrong, and you're leaving performance on the table, wasting fuel, limiting what your rocket can accomplish. It's a reminder that in engineering, details matter. The difference between good and great often comes down to millimeters, to tiny refinements that most people would never notice, but that make all the difference in performance. Engineers are working on a new type of rocket engine that sounds almost violent in concept, rotating detonation engines, where fuel doesn't burn steadily but instead explodes continuously in a spinning shockwave that races around the inside of a circular combustion chamber thousands of times per second. It sounds impossibly chaotic, like something that should destroy itself instantly. And yet, this design could be significantly more efficient than current engines. The idea is to harness detonation rather than deflagration. In conventional rocket engines, fuel burns, which is to say, it undergoes rapid combustion that propagates at subsonic speeds. But detonation is different. It's a supersonic combustion process, a shock wave that compresses and ignites the fuel almost instantaneously, releasing energy far more quickly than ordinary burning. In a rotating detonation engine, this shock wave travels around a ring-shaped channel, continuously consuming fresh fuel and oxidizer as it goes. The detonation wave never stops, it just rotates, faster and faster, creating thrust through the rapid, violent release of chemical energy. Prototypes have been tested, and they work. They produce thrust. They demonstrate higher efficiency than conventional engines, at least in theory. But there are enormous engineering challenges. The combustion environment is even more extreme than in standard rocket engines. The pressures and temperatures fluctuate wildly as the detonation wave passes. Materials must withstand not just heat and pressure, but rapid cycling between extremes. And controlling the process, ensuring the detonation wave remains stable, is extraordinarily difficult. Still, the potential is there. If rotating detonation engines can be made practical, they could revolutionize propulsion, providing more thrust from the same amount of fuel, making rockets more efficient, opening up mission profiles that aren't currently feasible. And maybe there's something poetic about that. We've been refining rocket engines for decades, making incremental improvements, optimizing nozzle shapes and cooling systems and combustion chamber designs. But sometimes, progress requires a fundamentally different approach, not refinement, but revolution. Not making the old thing better, but inventing something entirely new. There's a fundamental limit to how fast chemical rockets can go, and it has nothing to do with engineering. It's physics, pure and simple. The exhaust velocity from a chemical rocket, the speed at which gas exits the nozzle, can never exceed about 15,000 feet per second. No matter how clever your design, no matter what fuel you use. This limit exists because of the nature of chemical bonds themselves, the amount of energy stored in the molecular structures of fuel and oxidizer. When fuel burns, chemical bonds break and reform, releasing energy. But there's only so much energy available in those bonds. Hydrogen and oxygen burning together represent close to the theoretical maximum for chemical propulsion. The energy released per kilogram of fuel is about as high as chemistry allows, and that energy translates directly into exhaust velocity, how fast the combustion products shoot out the back of the engine. 15,000 feet per second sounds fast, and it is, but it's also limiting. It means that no matter how efficiently you design your rocket, no matter how perfectly you optimize your nozzle or your combustion chamber, you're always going to need enormous amounts of fuel to reach high speeds. The tyranny of the rocket equation kicks in, To go faster, you need more fuel, but more fuel means more weight, which means you need even more fuel to lift that weight, and the requirements spiral upward exponentially. This is why we'll never build a single-stage chemical rocket that can easily reach orbit and return. The mass ratios required are just too demanding. This is why interplanetary missions take months or years. Chemical rockets simply can't accelerate spacecraft to the speeds necessary for quick trips. And this is why researchers are exploring alternatives. Ion drives, nuclear propulsion, solar sails, technologies that aren't bound by the energy limits of chemical bonds. And chemical rockets got us to the moon. They've served us well for 70 years. But if we want to go farther, faster, if we want to make the solar system truly accessible, we'll need to move beyond chemistry, beyond the 15,000 feet per second limit that nature has imposed. The future of spaceflight might not involve burning fuel at all. It might involve fundamentally different ways of generating thrust, methods that work on different principles, that aren't constrained by how much energy you can extract from breaking and forming molecular bonds. Russia's Proton rocket has been launching since 1965, making it one of the longest-serving rocket designs in history. Think about that for a moment. The Proton first flew when Lyndon Johnson was president, when the Beatles were still recording together, when humans had not yet walked on the moon, and it's still flying today, more than half a century later, launching satellites and space station modules and interplanetary probes with remarkable consistency. The basic design has changed very little over those decades. There have been incremental improvements, certainly. Better engines, upgraded electronics, refined manufacturing techniques. But the fundamental architecture remains the same. 4 strap-on boosters around a central core, hypergolic fuels, a design philosophy that prioritizes reliability over innovation. The Proton has flown hundreds of missions, perhaps more than any other heavy-lift rocket in history. It's launched space stations, Mars probes, communication satellites, military payloads. It's failed sometimes. And yes, no rocket is perfect, but its success rate over decades of operation speaks to the soundness of the basic design. There's something reassuring about this longevity. In a field that often celebrates the new, the cutting edge, the revolutionary, the Proton represents continuity. It's a workhorse, a reliable tool that does its job without fanfare, without claiming to be the future of spaceflight. It simply works, and it keeps working, mission after mission, year after year, decade after decade. Perhaps that's worth more than we sometimes acknowledge. The flashy new design, the revolutionary concept, the technology that promises to change everything, those things capture attention and imagination. But the unglamorous rocket that launches consistently, that accumulates hundreds of successful flights, that proves its worth through sheer reliability, that has its own kind of value. The Proton won't inspire science fiction stories. It won't make headlines unless something goes wrong. But it will keep launching, keep carrying payloads to orbit, keep serving the purpose it was designed for more than half a century ago, and maybe that's enough. NASA's Space Launch System, currently under development, will be the most powerful rocket since the Saturn V. It's designed to lift the equivalent of about 27 elephants into orbit, roughly the same payload capacity as the rocket that took humans to the moon in the 1960s and 70s. And yet, the Space Launch System achieves this using engines and solid rocket boosters derived from the Space Shuttle program, technology that first flew in the 1970s. This might seem strange. Why build the most powerful rocket in modern history using decades-old technology? Why not design something entirely new, taking advantage of all the advances in materials science, computer modeling, manufacturing techniques developed in the intervening years? The answer is complex, rooted in politics and budgets and engineering practicality. The Space Shuttle main engines are proven, reliable, extraordinarily well understood. They've flown 135 missions without a single in-flight engine failure. The solid rocket boosters similarly have a long track record. Using these components reduces development risk, shortens the timeline, leverages existing infrastructure and expertise. But it also means the Space Launch System isn't revolutionary. It's not pushing the boundaries of what's possible. It's a very large rocket built using very mature technology, designed to accomplish specific missions, sending astronauts back to the Moon, eventually to Mars, using approaches we already know work, and perhaps there's wisdom in that, even if it's not exciting. Spaceflight is risky. Every launch is a controlled explosion, every mission a series of things that could go wrong. When you're planning to put humans on top of a rocket and send them 250,000 miles from Earth, reliability might matter more than innovation. The Space Launch System won't be cheap, it won't be reusable, it won't represent a breakthrough in propulsion or design philosophy. But it will hopefully work. It will carry astronauts safely beyond Earth orbit, doing for a new generation what the Saturn V did 50 years ago. Sometimes, the goal isn't to reinvent everything. Sometimes it's to take what worked before and make it work again in service of the next great journey. Most rocket engines use turbopumps to move fuel from the tanks into the combustion chamber. These are extraordinary devices, pumps that spin at tens of thousands of revolutions per minute, powered by burning a small amount of fuel to drive turbines. They're complex, expensive, difficult to design, and absolutely essential for high-performance rockets. But Rocket Lab's Electron rocket does something different. It uses electric pumps powered by batteries instead. This sounds almost absurd. Batteries? In a rocket? The weight penalty alone seems prohibitive. But Rocket Lab made it work, using lithium polymer batteries, the same basic technology in your phone or laptop, just scaled up and optimized for high power output. Electric motors drive the fuel pumps, eliminating the need for complex turbo machinery, reducing the number of moving parts, simplifying the engine design. The batteries are heavy, yes, but the simplification elsewhere in the engine makes up for it, at least for the Electron's small size and mission profile. And there are advantages beyond simplicity. Electric pumps can be tested thoroughly on the ground, run through hundreds of cycles to verify they work correctly. Turbopumps, by contrast, often can't be fully tested before flight. They operate in such extreme conditions that ground testing risks damaging them. Electric pumps also offer better control, more precise throttling, easier restart capability. The Electron has flown dozens of successful missions, easily proving the concept works for its payload class. It won't scale to larger rockets. The battery weight penalty becomes too severe. But for small satellites, for launches that don't require enormous thrust, the electric pump approach is viable. And perhaps that's a lesson about innovation. Sometimes the best solution isn't to make the traditional approach better. Sometimes it's to question whether the traditional approach is even necessary, to ask if there's a completely different way to solve the problem. Rocket Lab looked at turbopumps and asked, what if we just didn't? What if we used batteries instead? And it turns out, for their application, batteries work just fine. When rocket engineers talk about engine performance, they use a measure called specific impulse. It's essentially efficiency, how many seconds 1 pound of fuel can produce 1 pound of thrust. The higher the specific impulse, the more efficient the engine, the less fuel you need to accomplish a given mission. Chemical rockets, the best we have, achieve specific impulses around 450 seconds. That's the fuel burning in the most efficient way chemistry allows, producing thrust for 450 seconds per pound of propellant. Ion drives, by contrast, can exceed 3,000 seconds. 3,000 seconds of thrust per pound of fuel. That's more than 6 times as efficient as the best chemical rockets. But here's the catch. Ion drives produce vastly less thrust. Where a chemical rocket engine might produce hundreds of thousands of pounds of thrust, an ion drive produces a fraction of an ounce. You could hold your hand in front of an ion drive while it's running and feel only the gentlest pressure, like a soft breeze. So which is better? It depends entirely on what you're trying to do. If you need to lift off from Earth, to fight against gravity and climb through the atmosphere, you need thrust. Lots of it. Chemical rockets win. But if you're already in space, where there's no gravity to fight against, no air resistance to overcome, then efficiency matters more than raw power. You can use an ion drive, let it run for months or years, and eventually you'll reach speeds that chemical rockets can never achieve. It's a trade-off, a choice between power and efficiency, between doing something quickly and doing it economically. And maybe that's true in life beyond rocketry. Sometimes you need brute force, immediate action, or the ability to push hard and fast. Other times you need patience, efficiency, the willingness to work slowly toward a goal that chemical explosions alone could never reach. Different tools for different jobs, different engines for different missions, a single stage to orbit rocket, a vehicle that could launch from Earth, reach orbital velocity, and return intact without dropping any stages along the way, remains one of the holy grails of spaceflight. It's theoretically possible. The physics allows it. The rocket equation doesn't forbid it. And yet, despite decades of effort and numerous design studies, no one has ever successfully demonstrated a single-stage-to-orbit vehicle with the current technology. The problem is brutally simple. The mass ratios are unforgiving. To reach orbit, you need to accelerate to 17,500 miles per hour while fighting gravity and atmospheric drag. That requires a tremendous amount of fuel, and fuel has mass, and that mass needs to be lifted, which requires even more fuel. The numbers spiral quickly. When you run the calculations for a single-stage rocket using current materials and current engines, you find that 95% or more of the vehicle's mass must be fuel. The remaining 5%, or less, has to include the structure, the engines, the tanks, the avionics, the thermal protection, the landing systems, and any payload you want to carry. It's possible in principle, but only if you have materials that are stronger and lighter than anything we've yet developed, and engines that are more efficient than anything we currently build. Multi-stage rockets work because they solve this problem through discarding mass. You use huge engines and large fuel tanks to get off the ground, then throw them away once they're empty. The second stage, now lighter and at higher altitude, can be smaller and more efficient. Each stage is optimized for its portion of the flight, and the total mass ratio becomes manageable. But with a single stage, you're stuck carrying everything all the way to orbit and back. Every kilogram of structure is a kilogram of payload you can't carry. Perhaps someday we'll develop the materials and engines necessary to make single stage to orbit practical. advanced composites, revolutionary propulsion systems, exotic cooling techniques, something that changes the fundamental trade-offs. But for now, it remains tantalizingly out of reach. A goal that's theoretically achievable but practically impossible with the tools we have. And maybe that's a useful reminder about the limits of technology. Not everything that physics allows is something engineering can deliver, at least not yet. Sometimes the mathematics says yes, while the materials say not quite. Some rocket fuels are so toxic that exposure to even their vapors can be fatal within minutes. Hydrazine, nitrogen tetroxide, monomethylhydrazine. These chemicals attack the lungs, the nervous system, the organs. They can cause seizures, respiratory failure, cancer. A single breath of their vapors in concentrated form can kill. A spill on unprotected skin can cause severe burns and systemic poisoning. And yet, these substances have been used extensively in spaceflight since the beginning. Refueling a spacecraft with hypergolic propellants requires crews in full hazmat suits, working with procedures that rival bomb disposal in their attention to safety and precision. Every valve, every connection, every seal is checked and double-checked. The fueling process is slow, methodical, conducted with the awareness that one mistake could be catastrophic. Workers train extensively, practice emergency procedures, understand exactly what to do if a leak occurs or an exposure happens. The chemicals are transported in special containers, stored in bunkers designed to contain spills, handled only by qualified personnel who understand the risks. And despite all these dangers, hypergolic fuels remain in use. The Space Shuttle's orbital maneuvering system used them. The Apollo lunar module used them. Satellites, both commercial and military, may still use them for attitude control and orbit adjustments. The reason, as mentioned before, is reliability. When you absolutely need an engine to fire, hypergolic fuels work every single time. No ignition system to fail, no uncertainty about whether combustion will occur. The chemicals meet, they react, thrust happens. But perhaps there's something sobering about the fact that we're willing to work with such dangerous substances in pursuit of space exploration. The chemicals that can kill you are also the chemicals that enable certain missions, that provide capabilities no safer alternative can match. It's a calculated risk, one that space agencies around the world have decided is worth taking, as long as the proper precautions are followed. And maybe that speaks to the broader nature of spaceflight. It's dangerous. It always has been. We've made it safer over the decades, learned from failures, developed better procedures and equipment. But at its core, strapping yourself to tons of explosive chemicals and riding them into the vacuum of space remains one of the most hazardous things humans do. The fact that we do it anyway, that we accept the risks in pursuit of exploration and knowledge, says something about who we are as a species. The sound of a rocket launch arrives in waves. First, the sharp crack of ignition. That initial moment when the engines light and fire bursts from the base of the rocket. Then comes the sustained roar, a continuous thunder that builds and builds as the engines reach full power. And finally, there's a rumbling you feel more than hear, a deep vibration that resonates in your chest, in your bones, in your entire body. People who've witnessed launches up close often struggle to describe the experience adequately. Words like loud don't capture it. It's not just noise, it's physical presence, acoustic energy so intense that it seems to press against you, to envelop you, to become part of the environment in a way that normal sound never does. The air itself vibrates. The ground shakes. You feel the power not just in your ears but in your entire body, as if the rocket is reaching out across the distance and touching you with pure energy. From several miles away, the closest spectators are typically allowed, the sound takes time to arrive. You see the ignition first, the brilliant flame appearing at the base of the rocket. Then, a few seconds later, the sound reaches you, and it's overwhelming. Some people instinctively cover their ears, though it doesn't help much at these intensities. Others simply stand there, mouths open, experiencing something their nervous system has no reference point for, and even after the rocket has climbed out of sight, even after it's disappeared into the clouds or become a distant point of light against the blue sky, the sound continues. It echoes, reverberates, fades slowly rather than stopping abruptly. The launch is over, but the evidence of it lingers in the air, in the ringing in your ears, in the memory of that overwhelming physical sensation. Perhaps that's appropriate. A rocket launch should be loud. It should announce itself. It should be impossible to ignore. We're defying gravity, escaping our planet, sending something we built into the cosmos. That deserves to make noise. That deserves to shake the ground and rattle windows and leave spectators stunned and breathless. The sound is part of the spectacle, part of what makes spaceflight feel momentous rather than routine. And maybe we need that reminder, that physical jolt that tells us, yes, this matters. This is extraordinary. This is worth paying attention to. Despite 70 years of advancement in rocket technology, despite all our progress in materials science and engine design and computer modeling, we've never built a rocket more powerful than the Saturn V. Not for lack of trying, not because the technology doesn't exist, simply because we've never needed to, never had a mission that required that much capability. The Saturn V remains unmatched for deep space crewed missions, a testament to what were accomplished with 1960s technology and unlimited Cold War budgets. The Saturn V could lift over 260,000 pounds into low Earth orbit. It could send nearly 100,000 pounds toward the moon. Those numbers dwarf most modern rockets. The space shuttle couldn't match it. The current generation of heavy lift vehicles, while impressive, fall short. Only the upcoming Space Launch System approaches Saturn V's capabilities, and even then, it's essentially matching rather than exceeding what was achieved 5 decades ago. This might seem strange. Shouldn't technology improve over time? Shouldn't newer rockets be more powerful? But rocket capability isn't just about technology. It's about purpose. About having missions that justify the enormous expense of developing and operating ultra-heavy lift vehicles. The Saturn V existed because America committed to landing humans on the moon and had to build a rocket capable of that mission. Once the Apollo program ended, that level of capability wasn't needed anymore. Satellites could be launched on smaller rockets. Space stations could be assembled piece by piece rather than launched whole. The missions changed, and with them, the requirements changed. And so the most powerful rocket ever built was retired, its production lines shut down, its facilities repurposed. Some hardware still exists, test articles in museums, unused engines in storage, but the knowledge of how to build and operate the complete system has largely faded. The engineers who designed it have mostly retired or passed away. The supply chains that provided components no longer exist. If we wanted to build another Saturn V today, we'd essentially have to start from scratch, relearning lessons that were once well understood. Perhaps that's bittersweet. We reached our highest height decades ago and haven't returned since. but maybe it's also hopeful. The Saturn V proved what's possible. It showed that humans can build machines powerful enough to send us beyond Earth orbit to other worlds. We did it once, and if we need to do it again, when we need to do it again, we'll find a way. The knowledge might have faded, but the capability hasn't disappeared. It's just waiting, dormant, ready to be reawakened when the mission demands it. Every rocket that reaches space, regardless of its destination or purpose, crosses an invisible boundary called the Kármán line, located 62 miles above Earth's surface. This is where space officially begins, at least by international agreement. Below that line, you're in Earth's atmosphere, subject to aerodynamic forces supported or hindered by air. Above it, you're in space, where the rules change, where the atmosphere becomes so thin it might as well not exist. 62 miles doesn't seem like much in cosmic terms. It's a distance you could drive in an hour on a highway. But vertically, against gravity, fighting through an atmosphere that resists your passage, 62 miles represents humanity's most profound threshold. It's the boundary between earthbound and spacefaring, between being confined to our planet's surface and having access to the infinite beyond. When a rocket crosses the Kármán line, something changes. The vehicle is no longer flying in the traditional sense. It's not supported by aerodynamic lift. It's falling freely, in orbit or on a ballistic trajectory, subject only to gravity and momentum. The sky turns from blue to black. The curve of Earth becomes visible, the thin shell of atmosphere apparent against the darkness beyond. And for anyone aboard, crossing that line means becoming an astronaut, officially leaving Earth even if only briefly. Perhaps there's something arbitrary about choosing 62 miles as the boundary. Space doesn't suddenly begin at a specific altitude. The atmosphere fades gradually, becoming thinner and thinner until it merges imperceptibly with the vacuum between worlds. But we humans like boundaries, like clear delineations between one thing and another. And so, we drew a line at 62 miles and said, this is where space begins. This is the threshold you must cross to join the select few who have left Earth behind. Every launch, every rocket that climbs through the atmosphere toward orbit or beyond, is attempting to cross that line, to reach that boundary and move past it. And in doing so, each launch represents a continuation of a story that began in that Massachusetts cabbage patch nearly a century ago. The story of how we learned to build machines that could carry us beyond the world that made us, into the darkness where possibilities wait, patient and endless. And so we drift toward the end of this journey through the story of rockets, through these machines of fire and metal that carry our ambitions beyond the sky. From Robert Goddard's modest 2.5-second flight to spacecraft, hurtling toward the outer planets at speeds we can barely comprehend, rockets have been our way of touching what we cannot reach, of visiting places we cannot walk. They are violent and gentle at once. They shake the ground with thunder and yet navigate by starlight. They burn fuels so toxic that a breath could kill and produce exhaust, as clean as morning mist. They're built from the finest engineering humanity can muster, and sometimes they fail anyway, teaching us through their failures what their successes never could. Perhaps what's most remarkable is that we keep building them, keep refining them, keep pushing the boundaries of what they can do. Each launch is an act of optimism, a declaration that there's something worth reaching for beyond our atmosphere, beyond our gravity well, beyond the comfortable cradle of Earth. We send robots to Mars, telescopes into deep space, satellites that connect continents and help us understand our own planet better. And someday soon, we'll send humans back to the moon and eventually to Mars, carried there by rockets that trace their lineage back to bamboo tubes filled with gunpowder and a small vehicle that rose 41 feet above a cabbage patch. The journey continues, the rockets keep flying, and somewhere, right now, someone is designing the next one, solving the next problem, figuring out how to make the impossible merely difficult. Rest well, and may your dreams carry you as far as rockets carry us, toward horizons you haven't yet imagined, into darkness that holds more light than you can see from here. Good night.